Hello, my name is Tulen Thapa, and I have already explained, introduced myself. I'm a student of Delhi University, Ramjas College, semester 6, and today I will be showing you the rest of the code for statistical mechanics for Sem 6 in Scilab, which are very simple. Mainly all of them are very simple, but still we have some problems. So I already have made for 1, 2, 3 codes for first 3 codes. Now this is for the fourth code, but in this fourth code we when I was recording I had a little problem, and still I have not cleared the problem. So let's see where we left, and I have deleted that previous video that has gone wrong for the part 2, or this part that is going on. So I'm remaking it. So here it is, here it goes wrong. So what happens is what happened here is that we are doing for partition functions, है ना, partition function for नहीं we are doing for क्या बोलते हैं, distribution function for the Maxwell Boltzmann Fermi Dirac and Bose-Einstein Maxwell Boltzmann Fermi Dirac and Bose-Einstein's statistics, or you can say distributions. So clear CLG, CLF, these are the standards. We have given the values of k, that is Boltzmann constant that is divided by 1.6 into 10 to the minus 19. We can directly, firstly we should write its direct value in electron volts, that is 8.617. You can simply calculate by using dividing that. I have already written that I had wrote some time ago or few seconds ago before I have erased them. So this is 17 into 10 to the minus 7. So this is the value of Boltzmann constant in electron volts. Now we have taken T as 100, 500 and 1000, and we have taken E1 as minus 5 to 0.001, minus 5 to 0.01. We can take 0.01 and to 1, and we have given the value of mu as 0 and G as 1. So everything is fine. Now we have taken for let us write it again. So here, I suppose here where the mistake started. So this must be the same subplot. We are saying the subplot was not coming correctly. So now we will form two loops for I equal to 1 to length of, let us take length of LENGTH, length of T, and in the next loop for j is equal to 1 to 1 to length of, we can say we take the length of E1, that is the energy. We can simply take E also, where E is in electron volt, so I will take E. So now we simply have to put the formulas, and we have to put two ends also. So I put one end for first loop and second end for the second loop. Now I can simply put the formulas. I can calculate, I can take the formulas from when I have already noted down the formulas in the, or already made the code. So I will first go and copy that code, but only the formulas of it, because we only need the formulas. So I will copy these formulas because I need them. Let's say Control C. What happened? Control C, and we simply have to go and Control V. So here now let's see what happened. So firstly we have to calculate the value of alpha, because it will be used in the formula exponential a plus I. I can show you here. So here I have already told you, but I will tell you again, because it's my mistake, because I was not doing correctly. So what we are doing, we have for three distributions. So gi upon a ki power alpha plus beta ei. This is the for Boltzmann, Maxwell Boltzmann, our classical system, and we have second gi is equal to gi upon e ki power alpha plus beta ei, e ki power alpha plus beta ei minus 1. For this is for Bose-Einstein, and gi upon e की पावर अल्फा प्लस बीटा ई आई प्लस 1. दिस फॉर फर्मी डिराक, ये फर्मी डिराक के लिए, ये बोज आइंस्टाइन के लिए, एंड दिस वन इज फॉर मैक्सवेल बोल्ट्जमैन. And now we have also the value of alpha as minus nu upon kt, and the value of beta as 1 upon kt. So simply we have to put the values and we will get the result. So this is alpha's value minus nu upon kTi, and this is beta's value 1 upon kTi, है ना. Ti means the temperature change is changing, and j comma I, FMD j comma I means distribution function for Maxwell Boltzmann exponential a plus b into e1 jo, sorry, here we have taken e. So simply here and this, and according to this way this should work, and we have taken g's value as 1, so it should simply work. So it is showing undefined variable e1, so I have written e1 somewhere. There I have written e1, so here I will plot e1. So now I will run it again. So now it should show the correct graph. So it's not showing the correct graph because I have not replotted it. So we can see we have to replot from, this is for Fermi Dirac or this is for Maxwell Boltzmann. So we can put a replot. Replot is for replotting the graph such that we have a graph replot. Use this brackets and then use a bracket, square bracket inside it to replot. First 0 comma 0 is to the position of 0 comma 0 is show the position of x and the origin, where is the origin starting from, and the next two terms are up to which x and y should go. So this is x, and we have g's value 1, so y's value should be 1. So now let's see, this is for Maxwell Boltzmann, so it's correct, should be correct, should come out to be correct. First put f5 and we simply have to go and see. So there we can see that Maxwell Boltzmann's curve is coming out to be correct, and this subplot is used to form 2 cross 2 matrix in the graphical window. That is 1, 2, 3, 4. We have 4 space. Now we will see when I subplot it, subplot all of them. You will then see what I am saying, what I mean by this. So in the previous class the graph was not coming out to be correct, so I deleted it and now I'm plotting it again. So you can see this subplot, I can copy it and paste it, Control C, and we can simply change the variables, and we have to paste it 3 times. So first we have to change this term and this term. So this means that this show the position in the matrix. So it is like here it is 1, here it is 2, then 3, then 4. So it is like 1, 2, 3, 4. So now we have to we have to do for max Bose-Einstein, so BE, and here we have to do for Fermi Dirac. Now see to it that Fermi Dirac, the so replot has to be go from the axis, the origin has to be from -1 to 0, because the in Fermi Dirac we have the graph on other side of the you can say axis also, है ना. So we put this. If you plot the graph, you will not, if you don't put this, you will not see that characteristic shape of the Fermi Dirac. Fermi Dirac is like step size, step function, no? So if we now put plot it, so you can see the graphs are coming out to be correct, where this is perfect curves. Now you can use x label, y label, etc. And now if we have to plot for say, I will show you, for a single temperature and compare all of them. So we will put another Control V and we will put here 4, and now we have to compare all of them. So I will put like a square bracket, and then I will Control C and I will show you Control C, and I will put Control V comma Control C, Control V, Control C. We are simply plotting them together. You can say that, huh? We are not Control Z. We are not plotting them separately. Now you will see, but it will be very hectic because we have plotted all the curves here. Now if we want to plot a more clearer curve, so we can do, what we can do is take only one of the क्या बोलते हैं, one of the row or one of the column, whichever matrix it is forming. If it is forming a row or one of the column, because it generally takes in column. So first you can print FBE or FBE. If you print FBE, you will see what type of matrix it is forming. So here let us copy this, Control C and Control V, and now you will see what type of matrix is forming. It is forming a column matrix because of j comma I, na? So if we take first column, we have to take first column only. So we have to write double dot comma 1. We have to take first column only, na? So we have to write double dot comma 1. So we have taken first column. So now we can simply Control C and Control paste them, Control C and Control V. This means that we are taking only one of them, one of the column, one of the temperature, है ना? So here it is, backspace, and now it is correct. Or you can do the other way around if you can like, है ना? So now we see the temperature, the graph is coming out of this. But if you have to make it more separate, so you can take a larger temperature. You here we have taken one, you can take two. So what does 2 implies? 2 implies that it will see into the matrix of the temperature and see which temperature range is which temperature is corresponding to. So this is for 500 Kelvin. It is coming out to be more spaceful and more. It is coming out to be more vibrant. मतलब you can see what is the distribution in the what the various distribution look like in the same temperature for the same number of particles, or what the distribution looks like actually. So it is taking for 500, है ना? If I put 3, it will take for 1000. It will be even more space spacer because the distribution or the number of particle distribution in Maxwell-Boltzmann is the in Bose-Einstein is the largest. Then it is for the Maxwell-Boltzmann, and then it is for the Fermi-Dirac. Simply you can study this. Comparison: the curve between the density of curved particles and the energy values of the different distribution are plotted for a single temperature. In Maxwell-Boltzmann and Bose-Einstein, n number of particles can occupy a given energy level. Hence, there is no restriction in the number density of the particles. But in Fermi-Dirac Pauli exclusion principle, which restricts the number of the particles in the given energy level, the number of the particles occupying a given energy level is maximum for Bose-Einstein, then for Maxwell-Boltzmann, and then for Fermi-Dirac. These are the few restrictions that Maxwell-Boltzmann, because it is restricted to limited by the volume, energy, etc. physical restrictions, but such restrictions are absent in the Bose-Einstein. Hence, the number of the particles occupying a given energy is maximum in Bose-Einstein. Simply, it's meaning that Bose-Einstein does not have any restrictions on it. Maxwell, in a single state there can be any number of particles, but in Fermi-Dirac we have simply learned the Pauli exclusion principle, that no two particles of the same quantum number, no two electrons of the same quantum number, or same four quantum numbers can be can have the same four quantum numbers. That is, they must have at least three quantum numbers. If they have three quantum numbers similar, then their fourth quantum number, that is spin quantum number, that is should be different from each other, so that they do not occupy the same quantum state, है ना? So but in Bose and Einstein, all the particles can occupy the same quantum state, and in Maxwell-Boltzmann also. But in Maxwell-Boltzmann, there is classical particles, so there is volume, there is energy, there is limitation on other factors also. So Maxwell-Boltzmann's occupancy, or you can say Maxwell-Boltzmann number density of particles comes out to be less than Bose-Einstein's, है ना? Distribution function: occupy the same state, that occupy the same energy level. The distribution of the classical material particles over various energy states in thermal equilibrium. How many particles can occupy a given energy state? How particles are occupying a given energy state? N number of particles can occupy any number of energy and can occupy a given energy state in Bose-Einstein. So that's why you can simply say this, so that's why the distribution is so large. So that the curve is coming like this, है ना? Simply you can call this. So you can see that the curve is tending to infinity, and here this is known as the Fermi energy level. Above this, at 0 Kelvin, there are no particles above this. But as the temperature increases, there are particles above this, and as the temperature increases, there are particles above this Fermi energy level. But as the temperature but when the temperature is 0 Kelvin, there are no particles above the Fermi energy level. The Fermi energy level, you can say that is the maximum energy at 0 Kelvin, above which no particles are present, है ना? The energy of the state at which the देखो, you can say that it is the energy, Fermi energy is the energy of the state at which the highest particle is you can say that the Fermi at 0 Kelvin, the Fermi-Dirac system is alive. So there are many number of systems, है ना? So the Fermi energy, you can say that Fermi energy is like the the Fermi energy is the energy of the state at which the highest energy particle at the 0 Kelvin is placed, है ना? So this is the Fermi energy, and this is the Fermi level, and this is the Fermi of this below this, above this no particles are present at 0 Kelvin, and below this particles are present at 0 Kelvin. But as the temperature increases, particles jump from this state to this state, higher states, and hence the number of particles is symmetric, or you can say it forms a step function. This step function shows that above this energy there are no particles above 0 at 0 Kelvin. Here there are no particles at 0 Kelvin, and here there are all the particles at 0 Kelvin. But as the temperature increases, as the temperature rises, so what happens, this is the step function, so the particles here goes from here. This area and this area is equal because number of particles leaving the lower energy state and occupying the higher energy states are equal. So now we will again do the next part experiment, which is for, I suppose, what is it, for plotting the various parameters using the partition function. Partition function is like a mathematical tool. It has it's like the wave function of statistical mechanics, like the wave function phi is for the quantum mechanics. It can tell us the various properties like energies, entropy, and chemical potential, etc. for the system. So we have calculated it for a two-level system, that is minus nu b, two-level paramagnetic system in a magnetic field. So let us start first writing clear CLC and CLF. Now if I try to explain what is happening here, so it's something like this. Firstly, we have two particle level system, because when the paramagnetic material is placed in a magnetic field, it forms an angle theta. Its magnetic moment nu forms an angle theta which is equal to 5.780 to the power minus 5. This is the magnetic moments ratio, news answer news value. So here it is theta and there is the direction of b. So we have the magnetic force as nu b cos theta minus nu b cos theta. So when it is in anti-parallel position we have plus nu b, and when it is in the parallel position you can see it is 0 degree, and here it is come minus negative, so minus nu b. So here we have many formulas like z is equal to e की power nu b upon kt, nu b kt plus e की power minus nu b upon kt, and we have this can be written as e की power x plus e की power minus x, where x is equal to nu b upon kt, and this can be written as 2 cos h nu b upon kt. Then we have the formula for the partition, for then the formula for the pi upon p1 n1 upon n, that is p1, n1 upon n, that is p1 है ना. So this can be written as 1 upon 1 plus e की power e2 minus e1, e की power e2 minus e1, and here it is minus upon kt, and then n2 upon n1 can be written as n2 upon n1, n2 upon n can be written as 1 e की power same factor, this factor minus e2 minus e1 divided by kt upon 1 plus e की power minus e2 minus e1 divided by kt, है ना. Now we have the formula for energy. So we have various formulas. You can simply see, look them in a book. I am also writing them down here so that I also can remember them on the next exam. So we have magnetization. So magnetization is equal to nu square b upon kt. This is actually nu b upon nu tan h nu bar upon kt, where tan h nu upon kt when the temperature is high and the magnetic moment is low. So this tends to nu b upon kt only. So we have nu square upon kt because nu is also being multiplied here, and then we have formula for energy. Simply energy is equal to nu b tan h nu b upon kt, and then we have simply formula for S or entropy. So entropy's formula is very easy. So it is k log n, k log z plus E bar upon T, where E bar is this E bar and upon T. This is the average energy actually. And then we have formula for chemical potential, but I don't remember it. It has a formula for entropy, and then we have formula for one more thing, specific heat. Specific heat is a CB. So CB is actually CB is del E by del T, and here it is minus also, minus है ना. So CB is del E by del T, so you can calculate it. It's come out to be nu B upon kt का whole square into k. Here it is k, nu B upon kt into whole square. Here it is CB, and here it is sec h square nu B upon kt. Simple enough. Here it is written k nu B upon kt का whole square sec square nu B upon kt. You can differentiate and get this formula by directly also. And for S, I have already told you, here put the value of Z, 2 cos H nu B upon KT, and here put the value of A, E, that is above 1, that is nu B minus nu B tan H nu B upon KT. So this will come out to be, K you will take out common, so it will come out to be log nu B upon KT, log nu B upon KT, है ना, log 2 nu B upon, नहीं, log 2 cos H nu B upon KT. And then you can write simply minus nu b upon kt, minus nu b upon kt tan h nu b upon kt, because we have taken k common and t was already there in the division, so tan h nu b upon kt. So minus nu b upon kt, so minus nu b upon kt tan h nu b upon kt is e, and this term is coming out because we have taken k common and t is already been divided in the formula, that is s log z plus e upon t, and minus is already in present in e, here it is minus, there, therefore it is minus. So this is clear. So now we will simply put the values of constants. Here also we will take the constant as in electron volt. So we will have 8.617 into 10 to the power minus 5, and we have Nu's value as 5.78 into 10 to the power into 10 to the power minus 5. Now we will put B's values as equal to 1, B's values as equal to 1, B's values as equal to 1, and we can have E2 as, we can calculate E2 and E1. So let's just take caps lock E2 and like caps lock E1 and put their values equal to, so caps lock E2 would be equal to plus nu B, so let us take nu into B, caps lock B, and here it will be minus nu B, caps lock small u into B. So now we have already explained what are these and what will they do. So now we have to take temperature, we have to take a temperature range so that we can plot the graph. All of these are to be plotted against temperature, I suppose, है ना, if I am not mistaken, all these have to be temperature. So we will take a temperature range for specific heat. There is a different temperature range, and all of the rest of the above, all of them has this simple temperature range, that is 1 to 0.1 say 0.1 to 10. So all of them have the same this temperature range, and only for specific heat we have different temperatures, so we can write it into a different in a different for loop. So we can start for I is equal to 1, say from I is equal to 1 to n, 1 to length of I, length of t, length of t. It's as it is, it goes. Now we can simply, again I am doing the same thing, I am seeing the specific heat distribution functions. We can simply go to fixed experiment 2-level system and simply copy these formulas, and we can simply put these formulas. Now Bi is the beta, that is 1 upon Kt, where we have taken Kt1, so let us take T. Now Zi is equal to, we can simply put Z to as I have written is 2 into cos H, 2 into cos H nu B upon Kt, nu into capital B divided by into B. And why it is B? It is B because Kt is 1 upon B, Kt is equal to 1 upon Kt is equal to B, or Kt is equal to 1 upon B, nu B upon Kt, and we have 1 upon exponential d. Here we have not written d, so simply we can explain d. What is d? D will be equal to E2 minus E1, simply as simple as that, E2 control V minus control V, and here we have to write control E1. So D is D capital E is equal to caps lock E. Now we have explained what is D. Now D is equal to 1 by beta. P2 is B21 is equal to exponential D minus D upon B into beta minus D upon beta. Energy I is equal to minus 1 nu B nu B tan h nu B upon Kt. M is equal to nu square B upon Kt. I will give you another session. You can simply calculate the value of nu B and Kt, and it will be very simpler than this. and now you have to write SI is equal to K into log 2 into cos S nu B upon KT, cos S nu B upon KT minus nu B upon KT in tan S nu B upon KT. So this is correct, and now we can take another temperature range, that is T1 is equal to, now we can take T1, and now we can have T1 as 0.0.12, it is taken 0.1 only, है ना, 0.1 to 0.01 to 10. This is because the specific heat that the graph goes for like that black body temperature graph, that is first increases then decreases. Now we can simply have another for loop. Let's take for loop for j is equal to 1 to length of t1, length length of t1. Now we can simply put the again to see the formula and simply copy and paste it. Simple. The formula is very easy. CB, we have to again calculate B1, control C, we have beta, and again we have to again calculate the C, and again no, we have to calculate beta for this, for because the value of temperature is changing, so beta's value changing, so we have taken B1J, CBJ is equal to K nu B, B1J into 2 sec nu B upon KT का whole square. So this is the correct formula, and now we will run it. So first it will be asked to save the code. We have also not done. So this is the fifth one, video code fifth. So undefined variable t2. So t2 is not defined. So here we have to write t1. We have to also use the plot. Command. So here we write f5 and it is running, but it is not showing anything because and also the graph is not found because we have not used plot2d command. So now we will use 5 plot2d commands, and we don't have to replot in any of them. So we simply use, well, first we will use subplot and form a space for us. So we will form a 2 comma 3 comma 1, and we will copy it and paste it, control C, and paste it 6 times because there are 6 graphs to be formed. Control V, control V, control V, control V, control V. So these are the graphs. Control V, control, pen, enter, enter. So now we have for 1, we have for 2. So here I have to write here we have 3, here we have 4, here we have 5, here we have 6. So 6 graphs are to be formed. So now let us give what are to be plotted into each of them. So from in here we will plot PLOT, PL, sorry, my typing is a little bit sluggish now, PLOT. So here we will plot 2D. Use plot 2D command because it is much more accurate and more, I suppose, more features. It has more features. So let us see. First we plot Z, control C, T comma Z, T comma control V, and then we have to control C8 and control P V, control V, control V, control V, control V, control V. Now first we have Z, then we have, I suppose, Z P1 P2, control C. So second is for, so I suppose we have to use this for P1, caps lock P1 comma P2. This is for like plotting two graphs at the same time, two functions in the same graph, and this we have put then have to plot for energy. So we will simply control C8 and control V. So what we are doing here, we are giving the program what to plot. So like I am simply just replacing. I have simply just given it space to plot. This means that 2 comma 3 space will be plot. Matlab 2 rows and 3 columns will be there, and in one column, in one box there would be one graph. So it is will be M, and this is for capital S, and this is for CB. And now see to that CV has T1 temperature range, so here write C1 and here write CB, caps lock CB. And now you can run the program and undefined variable subplot. So I have written the spelling of plot subplot wrong, so remember to write in short. So subplot, 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 control Z, control Z, subplot subplot. So now I suppose it's correct. So now we will run it, and now we can see that the graph are being formed. Some of them are not getting formed correctly, but you get the idea. You simply have to put the formulas and you can get the answer. So let's see if we can correct it, and then go to our next code. So the only two codes are right, I suppose. Here it is, zi is equal to 2 into cos h nu b upon bi. It is correct, I suppose. Pi is equal to 1 upon 1 plus exponential. So let us see in which graphs are coming correct and which are not coming correct. So the first graph is not showing, and the second graph, this graph is for, I suppose, what is this graph for? I forgot. Fourth one. This is fourth one. So fourth graph is for magnetization. Magnetization is coming out to be correct. As the temperature increases, the magnetization decreases, and specific heat is coming out to be wrong, and entropy is coming out to be wrong. Entropy and energy is coming graph to be same. And the fourth graph is the third graph. Third graph is energy. Energy is coming out to be correct. Now let's see, s k into log h log 2 cos h nu b upon nu b minus nu b into bi. So you get the idea. You can go do it later on, because I don't have much time. My roommate will come and I cannot speak for too long. So let's jump into the next one. We will come to it later on if we have time. So now let's see what we can do. So we have this the sixth experiment. We have to plot for the part distribution of the part states and the occupation number with respect to the energy for the following relativistic and non-relativistic relativistic and non-relativistic bosons. So in it I have to explain a little bit. So let us see where we have space. Let us first go to home and file, home, and insert new page, blank 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 page. I am inserting blank page. You can insert blank page like it, but I also don't know how to how to actually erase them later on. So let us take which one where we have started. So let us take this one, है ना? It will take some time, so get ready. So firstly we have to see firstly we have to see draw. So firstly we have to see what we are doing. So we have the partition functions for uh, Fermi Dirac and Bose-Einstein as e to the power alpha plus beta e plus minus 1 plus minus 1. So minus 1 is for Bose-Einstein and plus 1 is for Fermi Dirac. Now we have the GS as 2 pi v. GS is the density of state upon h ka cube. The density of states is the number of the energy level that at a particular temperature is at a particular temperature is the number of the number of states at a given energy is the number of, I forgot the definition. I have to learn it because I have to write it tomorrow. The number of different states at a particular energy level the number of different states at a particular energy level that the particles are allowed to occupy is called per unit volume, is called density of states, and density of particles is the number of particles per unit volume with energy E between E and del E plus del E. Mathematically, it is the product of density of states and the occupation number. And what is this occupation number or distribution function? The number of particles present in a particular energy level. The number of particles present in a particular energy level. So we have GS density of state, the number of the particles that can occupy a particular energy level, the number of energy states at a particular energy level that the particles are allowed to occupy. The number of energy states at a particular energy level, number of energy states, different states at a particular energy level that the particles are allowed to occupy is known as the density of states. At a particular to occupy per unit volume is known as the density of state. So for non-relativistic particles we have 2 pi v h ka cube 2m ki power 3 by 2 and e to the power 1 by 2, and here we have dE, GE, here you have to write dE also, यहाँ पे dE. And for relativistic particles we have GEDE is equal to 4 pi v upon h का cube c का cube e की power 1 by 2 e की power e का square d. So this is for relativistic and this is for non-relativistic. Now we have to multiply the factor of gs of square due to the spin. So in relativistic we have 2s and in non-relativistic we have 2s plus 1 orientations. For a massive particles having spin, they have CVS plus 1 rotation, and for a non-massive non-massive particle and moving at the speed or velocity of light, they have 2s number of, they have simply 2s spin orientations. So now we get into what we have to do. Simply del n by del E is equal to, this is density of states, this is then density of state is equal to GE into density of particle is, this is density of particle is equal to density of states into occupation number, that is occupation number can be Fe. Simply simple as that. So we have the case for non-relativistic bosons, relativistic bosons, non-relativistic fermions and relativistic fermions. Now S for bosons is 0 and S for fermions is 1 by 2. Simple as that. And we have taken volume to be 1 here, and now we can simply do our code. And if we go into a little more detail, if I go into a little more detail, let us take an object of mass volume V and mass N. So now we have like distribution of its like this in 2D, and from this formula n ka square pi ka square h cut ka square upon 2 m l ka square is equal to e ka square. So now we can, what we can do, we can see is e ka square, e, there it is e, here it is, it becomes p ka square upon 2m is equal to h ka square pi ka square, and this n becomes nx ka square plus ny ka square plus nz ka square. These represent, this nx and y and z represent the quantum states, and the rest are m l ka square, this l ka, this r se r cancelled, this cancelled, and m se n m is cancelled. This l is I suppose remains the same. So and h cut, this h cut is changed into h, so there it is 2 pi ka square. So we have the equation as, we have the equation as p square is equal to h square upon 4l ka square. From here 4 comes and pi ka square is cancelled from above, so we have h ka square and nx ka square plus ny ka square plus nz ka square, and here it is 4l ka square into 4l ka square. So this is like a equation of a sphere with the radius of 4l ka lp 2lp upon h. You can simply see the radius of the sphere is 2lp upon h. This is x ka square, sphere of the sphere, x ka square y ka square plus z ka square, and here it is h, here it will go h, and here it will go 4 to 2l ka square. So when we will take under root, we will get 2lp upon L2lp upon h. This is the radius. Now what will be the number of states occupying? So we can simply calculate by 1 by 8 into 4 by 3, that is a volume of the cube, 4 by 3 pi 2l upon 2lh 2lp upon h ka whole cube. So we will have this term 4 pi v, l ka cube is v upon 3h ka cube into p ka cube. So now del phi upon del p is equal to density of states. In terms of density of states, you can write Gp in terms of momentum space, in terms of momentum. So we have 4 pi upon 3h ka cube, 4 pi v upon 3h ka cube p ka square. So this term is very important, 4 pi v upon 3h ka cube, and this term is very important. So in this term, if we put p is equal to under root 2 me, and if we put p is equal to under root p is equal to E upon C. So if we put E upon C, we will get formula for the non-relativistic, and if for P is equal to under root 2 me, we get formula for non-relativistic density of states. So we will get dg for relativistic and non-relativistic. Now we can simply multiply it by 2s plus 1, and so we multiply this by 2s, and then we can multiply it by the occupation number, or simply the number of particles occupying a particular energy level, है ना, number of particles occupying the particle present in a particular energy level, and number of particles present in a particular energy level, that is represented by occupation number, the number of particles present in a particular energy level. So we can multiply by the respective occupation number and get the desired formulas, and we can write these formulas and do the we can write the formulas and do the codes. So now let us write clear CLC CLF. Now we have to, this is codes number 6. Let's save it as first only. Now we have to simply we have to now simply first define the value of the constants. So from here onwards, so till here, that is, I will let you know from where to where we have to take electron volt. This is very confusing task. So specific heat, from till specific heat solid, take K is equal to 1.38 and H is equal to same, and from Bose-Einstein's take K is equal to 8.617 to the minus 5. This much I have understood there from here, from my copy. So let us now take for density state for relativistic on non-relativistic bosons and fermions. Sorry, I'm a little tired. I'm yawning a little bit. So now let us start. So we have K is equal to 8.617. We have K is equal to 8.617. That is value of the Boltzmann constants in electron volts into 10 to the power minus 5 into 10 to the power minus 5, and then we have H is equal to H values in electron volts 4.137 1357 into 10 to the power minus into 10 to the power minus 15. So these are values of our constant. Then we can define value of C also. C is equal to 3 into 10 to the power 8. And now we have defined C. Now we can define volume is equal to 1. And now we can also define temperature. We will take two temperature for the comparison point of view. So we have taken two temperature, 100 and 1000. Now we can calculate their length, and we have to take something that is on the x-axis. So in here we have x-axis, on x-axis we have E. So we have energy ranging from 0 to 0.01 to 2. Simple as that. And we have display the length of the choice, enter their choices. You can for conditional statement, but I will show you for simple things. So E is equal to 0 to 0.01 to 2. So I will show you for a once, and you can do it for the rest of them by yourself, I suppose. It will be a long task, man. It will be a long task. It has been a long day, man. So let us take the case for let us take for we are taking the case of I will do for relativistic and non-relativistic both, I suppose. Bosons, so I will take bosons. Okay. So for bosons, S is equal to, you can predefine S as well. For predefine S as 1, and then G would simply be, so G1 would be simply be 2 into S plus 1 for relativistic, and G2 would be 2 into S. So meaning that G1 would be 1 and G2 would be 0. For relativistic, we can simply write it down. For relativistic for non-relativistic. So now we have values of GS and GS, and now we have also value of what we have. We can define value of V as 1, and V has already defined value of V as 1. What we can do is define the value of, for bosons we have to take like we have to take for mass also, no, for bosons mass also we have to take. So let us see what I have done for bosons. What is the, where is the DOP? 2m to the power density of states for non-relativistic bosons. So here would be, where would be mass? So for the bosons we have taken, I have simply explained it using the code I have made because it's too long, man. So let us see code for the experiment, 12 graph code, and this is also 1 2 3 4 5 6 7 8. So only 7 graphs. So 18 graph one is the one we have to take. So let us see what I have done in here first. Let us see as a result for first or second. Let us see what changes I have made. Okay, okay, I am understanding a little bit. So it was a long code, but I will explain it. So first we have taken the value of first we have taken the value of k and h. First we have taken the value of k and h. Uh, K and H in electron volts. Then we have chemical we have taken C and V as my one. Then LT is the length of T and E is equal to 0 to 0.001 to more number of points are being taken here. So L is the length of E and display your choice. Enter your choice. This choice is for like this. For if you I have made a choice for like if you want for relativistic and non-relativistic fermion to enter one, and if you plot if you enter anything else you will plot for non-relativistic and relativistic bosons. So let us take you have to put tool is equal to 1 and I have named the variable as tool. You can name it that anything like name it as name it like anything, and if you put tool is equal to 1 then s and put s is equal to 1 by 2. Then for we are doing for non-relativistic and relativistic fermions. This part of the code in the tool is for plotting relative graph for relativistic and non-relativistic fermion. So S is 1 by 2. This is simple. Then J is equal to 2s degeneracy for the relativistic particles. So M we have taken for electrons for because fermions weighted example is electron. U is equal to 1. Value of the chemical potential for the fermions is 1 and value of chemical potential for bosons is -1. You have to remember that. And remember the range also 0 to 0.01 into 2 to for I is equal to 1 say LE, the loop is changing for the values they go. So for from 1 to LT, for this for changing the values of T and for changing the values of energy. So we have first calculated the density of states for relativistic fermions. This is the formula GS1 4 into power for relativistic fermions 4 into 4 pi v upon h ka cube upon c ka cube 4 pi v h ka cube upon c ka cube e ka square. So this is for relativistic fermions. Then we have calculated B and AL B and alpha. So we can calculate NJ and F. So 1 plus alpha alpha J plus beta E plus alpha E plus 1 fermions, and this we have simply calculated density of particles or relativistic fermions as NFGI coming to DOS or क्या होता है NFGI into density of states or relativistic fermions. So I put dot into multiply here because dot into multiply means the multiplication would be done so in such a way that multiplication will be done in such a way that uh, with the matrix are like overlap each other, and those particles those terms that are coming together are multiplied. Not this is not like the simple matrix multiplication. If you put simply the star here, it would be like the matrix multiplication, that is taking a row and taking a column. You can understand it. The dot star means that one term will be multiplied with another term. So I have used this. GS2 is equal to 2s plus 1 degeneracy factor for the non-relativistic particles, and again we have particle density of state for non-relativistic fermions, and we again calculated this, and density of particle for non-relativistic fermions, and again we calculated this. Then density of particle, density of state for non-relativistic fermions, density of particle for non-relativistic fermions is simply NJF J comma I. Density of state for non-relativistic fermions. Remember to use dot into star because there will be it will be like a two matrix two I suppose matrix, it will be like a matrix. So we have to multiply a single term with a single term. That's why we are using dot in DOP formulas, and rest of them we have to write simply multiply only. We can write simply multiply only. Subplot 2 comma 3 comma 1 density of spherical in. We have again for then the same for the for bosons. Simply multiply and just simply multiply with dot star in DOPRB. Simple as that. And again we have subplotted. And this is because density of states in fermions we have DOPRF. In fermions we can compare them because NF and 1 comma I we can compare them, but in bosons it was coming out to be differently. So we have to write this code 3 times and we have to plot them for plot them for 3 different, and hence eating graphs are formed because this term was not this was not happening in the bosons. You can see I have written for this bosons. This is to because the ranges are different. For bosons this DOPNON B relativistic bosons, it is coming out to be in different range, and this is coming out to be different range. So if you plot the graph together they get adjusted, and the one of them is shown and another is not shown. So if for showing them both, we have to plot the graph in different windows or different windows, and we also different conditions we also have to replot them I suppose. So here replot is not needed, here replot is not needed. So here replot is needed because here क्या बोलते हैं, replot is needed because the graph was not being formed and my Bharat sir helped me out here. So I don't understand a little bit here, but I understand the code fully, and but I don't know how he correctly found this value term. We are looking at the graph only, but I don't really get it, है ना? So we have these graphs, and you can now be free. Mm. So let us write file save as in Statistical Mechanics Labs. Let us name it as for video purposes, so I don't accidentally forget it. So now let us again come back here. So now we will form again the seventh code. This will be the last one, and I don't really understand the Pro. I will like go like randomly there. Clear CLC CLF again. Now we simply have to, but now in this one we have to take the original values of k. So for the first three we have to take k, and and the last one we have to take k. Middle three we have to take k's values as in electron volts, I suppose. So this information would be very helpful when you are doing code in the Scilab programs in the real examination, है ना? So up to code 3 we are taking case values at. I will again look at. So first in the first code there is no value or need of k. In the second code value of h is and k are in not in electron volts, in normal joules, or you can say normal units, and in specific solid it is also the same. And now in the fourth code it is where it is starts changing its values. K's value is 8.6, 8.6, and in this here also the K's value is 8.6, and pH value is H value is also according to it. But in the last one we have K's values of 1.38. So first one doesn't matter. So first two, and the first two, three, and is last seventh, and in the middle ones they have the values of K's as 8.617, I suppose, 8 to the minus 5. So here again 1.38, we have again come back to our original value, the street value that we remember, that we don't have any worries to work with. So we can simply write the value of Boltzmann constant. Now we write define a temperature range because we have to form a graph. So let us take 100, 500, and 1000. So if anybody on the outside world is has been following me up till now, you can say hi, because I want to know how many, if even I am reaching someone or not. You can say anything, man, anything. Just ask me what anything, why I'm doing my push-ups. It will make me a little happy. So let's not diverge it from it, diverge from our topic, and now let us see what we can do. We have t. Now we can calculate the length of t, which we don't have to calculate. I usually calculate in my other programs. Now we have the mass of oxygen. We can directly note it down from my code. So this is the code, you can see, and we are taking the mass of the oxygen here. I will explain it completely, man. This one is a little shorter, so I can explain it. So this is the mass of the oxygen atom, and now what we have to do is we have to take a new file. Sorry, file open. So here, so we have these formulas. We have the formulas this like I will take this one. So we have the formulas like we have the for these formulas. So the distribution with the velocity, the speed distribution function is the speed distribution. Sorry, we don't have space here, so let's go down. So here we have space, home, insert draw. For speed distribution, we have like the speed distribution as 4 pi. What is happening here? What is happening here? I don't know what I did, but I did something wrong, I suppose. What is happening? So now let us see what is happening. We have the formula. I forgot the formulas. I generally don't forget the formulas, but I forgot the formulas. What will I do in the next 2 days, tomorrow's exam? I don't know. But let's see what was the formula. So this was the formula: 4 pi m point 2 pi kt to the power 3 by 2. Oh my god! My god! Again I have to write down 4 pi 2m to the power. No, 4 pi 2m to the power m upon 2 pi kt to the power 3 by 2 v का स्क्वायर e की पावर mv का स्क्वायर माइनस mv का स्क्वायर अपॉन 2 kt. दिस इज द मैक्सवेल वेलोसिटी डिस्ट्रीब्यूशन, मैक्सवेल स्पीड डिस्ट्रीब्यूशन, सॉरी स्पीड डिस्ट्रीब्यूशन, मैक्सवेल स्पीड डिस्ट्रीब्यूशन सिंपली फॉर a system or particles. You can say that kinetic theory of gases, the gaseous systems or the gas in a gaseous system, molecules are in random motion, so they are exhibiting different speeds, energy, momentum, velocity. Maxwell-Boltzmann distributions are the probability distribution of the particles of ideal gas over particles of the ideal gas over the various energy, speeds, momentum, and velocity. Maxwell-Boltzmann distribution are the probability distribution of the particles of an ideal gas over particles of an ideal gas over the various energies, momentum, and velocities. Maxwell-Boltzmann distribution is like are the probability distribution of the particles of an ideal gas over the various energy. This means they show that how many particles will show this much velocity, I suppose. Now let us see an example like I can draw. Uh, if I draw like if I have most probable speed would be, I forgot what would be, 2 kt upon m. RMS speed will be 3 kt upon m, and my scroll doesn't work, so hence I have to uh, do it manually. So and we have under root 8 kt by m as the 8 kt 8 kt upon pi m 8 kt upon pi m as the average speed. So let us now simply see what is happening here, and we can simply make the code. So now we have to take a velocity range. Velocity range in this, if I remember it correctly, I suppose 0 with 5 divisions, 5 and up to 3000. This means that it will go from 0 to 3000 with a step size of 5. That is, it may have many number of term velocities. So now we can simply put a for loop for t and for v, and we can put the formula. So we put a for loop of I is equal to 1 to length of t, and we put for j is equal to 1 to k 1 to m 1 to sorry my brain is lagging. 1 to length of v. So now what we have to do, we put end here because there are two loops, so we put two ends here, and now we simply have to put the formula, which I can simply I have already made this program, so I can simply control C and control V. So this is the formula, and I go here and I put it here. So this is Fs is equal to matlab Maxwell's velocity distribution, speed distribution function. 4 into percentage pi means 4 pi upon 2 pi kt to the power 3.5. This can be written as 3 by 2 v to the power v ka square exponential v to the power I. So I have taken j as I, and I have taken for we have taken this. So I will put it here I, and I will put it here j, and I will put here j, and put here I. So it is correct formula. You can see 4 pi m upon 2 pi kt to the power 3 by 2 v का square e के power minus mv square upon 2 kt. 4 pi kt 4 pi kt 4 pi kt 4 pi kt. So no, sorry 4 pi m upon 4 pi m upon 2 pi kt 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 4 pi m upon 2 pi m upon 2 pi kt to the power 3 by 2 v square e to the power minus mv square upon 2 kt. V average is equal to 8 kt by pi m. V rms is equal to, this is, we have to see what will going on. So first we will do this, and we simply have to display, we have to plot 2d. We simply have to plot between v comma fs, है ना, and we will have a graph. So we will plot and we will write is 7 video 7 video code 7, and we will run it, and it should come out to be correct. So this is not coming out to be correct at all. So we have to see what so the graph of the speed distribution should be coming out to be like this. So it should come out like this. So it should come out like somewhat like here is velocity distribution, and here it is velocity speeds, मतलब speed distribution and it is speed. So this is for temperature T1. As the temperature increases, it keeps on decreasing in altitude, and this is for T3. So this is T3, this is T2, and this is T1. As the temperature increases, the peak velocity decreases, but the average velocity, total velocity of the particles, मतलब average energy of the particles increases, but as the total speed decreases, the maximum speed decreases, the most probable speed decreases. We can see what we have written in the result for to first understand what is going on. Initially, curve for every increases indicating the number of particles having higher or more increases and up to a certain value, and velocity of the particle is the most probable speed of the particle. Most probable possess speed of the maximum number of the particles. After reaching most probable speed, maximum number of particles possessing higher speed states to decrease. With increase in the temperature, number of the particles corresponding to the most probable speed decreases, and the average speed of all the particles increases. This can be understood from the Maxwell distribution for the speed f is equal to 4 pi m upon 2 pi kt to the power 3 by 2 e to the power minus mv square upon 2 kt v square mv square upon 2 kt mv square into 2 upon 2 into 2 kt mv square upon 2 kt. At low speeds, mv square upon 2 kt into mv square upon 2 kt dv. अच्छा, v square is also there, so v square is here. At low speeds, exponential minus mv square upon 2 kt is nearly equal to 1. mv square upon 2 kt is nearly equal to 1. Hence at given temperature, s speed is equal to v square. This causes the increase in the fe with v. At high speeds, exponential minus mv square upon 2 kt is the dominating term, which causes the decrease in the fe with the increase of the v. Also, fe is equal to 1 upon t to the power 3 by 2, and at given speed, hence if we increase the temperature, the fe decreases. How many, this shows how many particles of most probable velocity speeds. It shows this is most probable speed. As the particle as the temperature increases, randomness increases, and most of the particles have more speeds, but no, not that many particles have the same speeds. So particles tends to have more speed because of energy increase, but they collide with each other, and hence not a constant velocity can be maintained, and hence the speed, the most probable speed goes down very fast, I suppose. So now this graph is coming out to be wrong. Let's see what is going on. 05 to 2000, 3000. Let us see what I have done. 05 60,000, 32 into the power 1.6 into the minus 27. Fj comma I is equal to, let us see the function fs, what its value is. So its value is coming out to be like correct also in terms, I suppose. Fs is equal to j1 comma j1 से 4 pi per pi into vj square. Vj मतलब vj square m into 2 pi k ti. Sorry for the disturbances, because here many domestic violence is a common case, I suppose, in Delhi. Every day there is a riot, I suppose, a small riot, I suppose, in the houses only. A small fight, man, I suppose. 4 pi m upon 2 pi kti into e to the power 3 by 2 v to the power square exponential minus 1 mth. So we have to do this only, and then I don't have much power, so what we have to do is find the maximum mode. So we can write this like this, a comma b, and we can put into a for loop for calculating for all of them. So we put them into a for loop for j, for which for used for I. So we again put it for like this, control C, and we put it for control V, and we control V, and we control V. Sorry. We now put A comma B is equal to max of. So this code will give us the maximum value, the maximum of the maximum of the curve. So we write fs, maximum of fs, j comma j means we are taking the complete row. So we can suppose we are taking the complete column, I suppose. So complete column, for taking complete comma we take j comma 0 double dot, I suppose, j comma double dot j. This is mean that we can see max value of this into b, and this b will be and this b will give us the maximum value v experimental means v most probable speed. This will give the most probable speed. V most probable speed experimental is equal to v most probable speed experimental, v most probable speed experiment j, v most probable speed experimentally j is equal to, we will have v of b. This because b is the index of the maximum value of function, है ना. Sorry, my teeth is in a little bit pain too. Or much, a lot of pain. So you get the idea. We can do this and get the value of fs, maximum of fs. Then that will be, this will be v exponent v experimental. Then we have the formulas like for experimental, for theoretical. For theoretical, you can calculate using 8 kt upon pi m. We have pi, we have m, we have k, we have t. So for experimental, we can calculate this. So t will cheat for t if we have 100 and 1000, na 100 and 1000, or what we have t 100, 500 and 1000. So you can calculate it using this, and we have 2 kt upon m as the most probable speed, and 3 kt upon m as the root mean square speed. And for experimental value, we have found this the most, sorry, we have found this the most probable speed. नहीं, we have found the most probable speed, है ना, most probable speed, we have found the most probable speed. This is average speed, this is most probable speed, so we have found this. So we have found the kt upon m's value, root kt upon root 2 kt upon m's value is equal to v most probable experimental most probable. So we will simply put as divided by root 2 and get the answer, I suppose. Let me see if I am correct or not, but I am thinking is correct or not. So simply put q is equal to 1 upon 2 root 2 into exponential. So I am correct. So we get the value of v most probable, है ना, v most probable experimentally. So we can calculate the value of root kt upon m from here, and then we can calculate the rest of them by multiplying it by 8 by pi. So 8 by pi into kt by m will be give us v average speed, है ना. v 8 by pi into v, again I will look into it. So I don't do v average is equal to under root 8 kt upon pi m, and v most probable is equal to under root 2 kt upon m, and v rms we can also calculate v rms by multiplying root 3 into under root kt by m. So it is as simple, and then we can see to it whether the these two are coming out to be same or not. We can see whether these two values are coming out to be same or not, and then we can say that experimental value is then we can, what we can say is experimental values of vrms, v average, and what is this vrms, and what we have got vrms, v average, v most probable, vmp are coming out to be same as their theoretical values, their theoretical values. Hence the Maxwell speed distribution is proven, or you can say we have seen that it works. Thank you for everything and listening to me so far. It's been a very hectic day because I was very tired and I want to play a little bit, but the roommate would come and tell me to shut up. So I have to end it at this note. So I have done my push-ups for today. I will upload it, I suppose, at night. And this is all for today. My name is Student Tapa. Signing off. Bye. Signing off for now. Signing out. Signing out for now. Thank you.